My name is Tejas Kokje, and I am the founding engineer and head of engineering at Middleware. Before Middleware, I was at Netflix working in their cloud infrastructure engineering team, working on the network observability tool. So what I'm going to talk today is how we leverage ClickHouse to build our observability platform and how we scale it, and what are some of the challenges that we run into while using ClickHouse. So before I do that, let me give a quick plug on what is Middleware. So we are full stack cloud observability platform. So we provide dashboards to monitor your logs, metrics, traces, alerts. You can use middleware for your application performance monitoring for applications written in Go, Node, Java, PHP, etc. We have infrastructure monitoring for your Kubernetes, Linux instances, Docker, PCS, Windows, etc. You can test the availability of your services using our synthetic monitoring from various regions all across the world. And you can also monitor how users are interacting with your website or your mobile apps using our real user monitoring product. We are 100% OpenTelemetry compliant. So if you're already using OpenTelemetry, just few lines of config change and you can start using middleware. How are we different? We provide ingestion controls for the lower levels of your signals. So you can pick and choose what logs you export to us, what metrics are being collected by middleware. And we are identity-centered observability experience as opposed to signal-focused. So we oftentimes, all you know is your service is down, you know the service name. We provide you a search kind of an experience where you plug in the service name and we can show you everything we know about that service. So that's the experience we are aiming for with middleware. Before I explain you how we use ClickHouse, let me just quickly show you our architecture of the services. So here we run everything on Kubernetes. Even ClickHouse is run as a stateful set on Kubernetes. On the left, you will see we have our agent/APM, which is running in customers' infrastructure, sending us the telemetry data. It comes through a load balancer, and it goes to the ingestion layer. So the green line is all the telemetry data, and the black line is all the dashboard and the consumption of that telemetry data using our browser, using your browser. So what happens is all your telemetry data is coming to the lower bottom ingestion layer, and we'll be focusing mostly on the lower ingestion layer today. But once we collect the data, you can consume the data using your browser. You can log into the website. We have API layer. We have live streaming of your telemetry data so that we show them to your browser. So for ClickHouse, we do use S3 as our cold storage. So there is some hot data worth 2 weeks of data that lives on ClickHouse, but then we use S3 backed storage policy in ClickHouse to dump all the cold data to Amazon S3. And I'll be talking more about what are some of the parameters that we use to dump the data. Going to the next slide. So we saw in the previous slide, we saw that there was an ingestion layer at the bottom, which was consuming. Actually, let me go back one more time. But there's Kafka, which is our pub sub. And then we have a collection of service called batching service. And I'll tell you why we need batching service. Why didn't we use ClickHouse's Kafka ingestion to directly consume from Kafka? So, and in the next slide, I'll be talking in more details about the bottom 4 services. So on this slide, I've enlarged the Kafka and the batching service. So what happens is on the ingestion layer, all your telemetry data is being streamed in on the ingestion layer. And in the ingestion layer, we have collection of microservices, one for logs, one for metrics, one for traces, and one for continuous profiling. So imagine the ingestion layer box on the left is a collection of microservices, and your telemetry data is being streamed into that layer. And what happens is, depending on your data type, be it logs, metrics, traces, one of the services picks up the data and hashes based on the account ID. Each customer gets an account ID. So each telemetry data belongs to a customer, and we hash it and pick a Kafka partition to send the message into. So as you can see in Kafka, we have logs, metrics, and traces topic separate, and each one of them have their own partitions. So depending on the hash of the customer ID, we will end up picking one partition, and then the batching services are the consumers of those messages. So each batching service has multiple replicas, and each replica consumes from one partition. So technically what it means is each replica is responsible for one customer's traffic. Right? So, and the reason we have this batching service is ClickHouse, we use merge tree engine, specifically replicated merge tree engine in ClickHouse, and ClickHouse does not like frequent inserts of our merge tree. The reason being, every insert creates a part, what is something called a part in ClickHouse. And if you are doing 100,000 inserts, it is going to create 100,000 parts. And behind the scenes, over time, ClickHouse is going to merge those parts. So it's for efficient processing. So more parts you create, the more meta work that you create for ClickHouse to merge. So it is ideal to batch and create less inserts so that less parts are getting created in ClickHouse, so that ClickHouse has to merge less. So today what we do is all these batching services, they buffer the traffic, buffer the messages either for 30 seconds or till the data size hits 200 MB. We don't want to buffer for too long because then it delays ingestion into ClickHouse, and that might delay users' experience when they go look at their observability data. So there is a fine balance that needs to be struck here for how much to buffer. And we also don't want to insert again too frequently because then it unnecessarily consumes ClickHouse cycles, and we see the performance impact on insert queries going down because ClickHouse is just busy doing the meta work. So we are a self-hosted ClickHouse. We self-host the ClickHouse, and the way we deploy, again, as I said, everything runs in Kubernetes. And for ClickHouse, we run it as a stateful set. Currently, as of now, we have 4 shards replicated across 2 availability zones. Each of those machines are 64 cores and 120 gig memory. As I said, they are stateful sets with dedicated nodes on each of these stateful sets. So all these Kubernetes nodes are dedicated just for ClickHouse. Use Kubernetes node selectors, taints, and tolerances to make sure no other workload gets scheduled on these nodes. And if you observe, each one of them is a different stateful set, but in the same namespace for a given shard. The reason we did it is because the configurations are different depending on the shard and the availability zone, right? So like, for example, in this picture, I have shown there's 3 buckets, which are different for 2 availability zones, US East 1A and US East 1B. But there are a bunch of other configurations, internal configurations that are also different for different shards and different availability zones. So we figured it's easier to manage if you just create a separate stateful set and have the configuration in those stateful set config YAML files. One thing I haven't shown here is the magic of the replication that is happening because we have 2 nodes per shard. So these are replicated nodes. And the ClickHouse keeper, there is a cluster of ClickHouse keeper that is running to ensure that the data is replicated across both replicas. So 4 shards, 2 replicas for per shard is what we have right now. Coming to how we store data. So we have one database per customer, and one we hash the database or hash the customer so that they end up in one of those shards. So then what it means is you can either be in one of those 4 shards that I shown that we had before. So one database per customer. It also allows us to configure custom configuration per customer. Some customers want us to retain their data for longer. Today, as I said, we retain 2 weeks of hot data on the servers and 6 months of cold data on S3. But some customers might want more data to be retained for a year or more hot data. And having a separate database allows us to fine-tune that. We have separate tables for logs, metrics, and traces. The reason being these 3 are different signals, different schemas for them make sense. Logs are not much aggregated. Metrics are heavily aggregated. And same for traces. They are like logs, so not so much aggregated. We use replicated merge tree engine for all the raw tables, so that the replication is taken care by ClickHouse Keeper. You saw that there were 2 replicas per shard. So that's where the magic happens. And we heavily use materialized views for aggregation. Like replacing merge tree engine in one of the materialized views where we want resource attribute views. For example, when your service sends a log, typically there is a message that XYZ happened. And then there is a lot of metadata that, this log was generated on this host ID in this region for this service. So and we provide you a dashboard so that you can filter based on those metadata. So we have to create a view so that those dashboarding queries are faster. So we create the materialized view for replacing merge tree because we don't want attributes to be duplicated. Because in ClickHouse, what we learned was primary key is not like your relational database primary key. Primary key can have duplicates, while in relational, primary key cannot have duplicates. So that's why we have this replacing merge tree, which sort of consolidates all the duplicate keys, and we have one row of attributes per log. And then aggregating merge tree for metrics. Metrics are most of the time aggregated over 15 minutes, 1 hour, 2 hour, whatever the time frame be. So aggregating merge tree for aggregating CPU and memory, so that when you log in, we show you, hey, how was your CPU consumption for this host over last 1 hour? Those are pretty fast if we have pre-canned materialized view showing you that data. Again, as I said, hot data is for 2 weeks on the server, cold data in S3 using S3 backed storage policy. Nothing fancy here. ClickHouse already provides this out of the box. Data retention is configurable because we use separate tables. And as previous speakers have also shown, most like partitioning table by timestamp is the best way to partition your data, because one thing, observability data is always in the context of a time frame. You always want to know what happened to your service, to your server over last 1 hour, 5 hours, or whatever that time window is. So any observability data is always in the context of a time range. So what this allows us to do is, if you partition your tables by timestamp, ClickHouse creates one partition per day. So here we partition our tables per day, so per date. So every day ClickHouse creates a new partition for us, and it keeps merging the parts within that partition whenever the inserts happen. And all within this partition, the data is also ordered by an hour. So what this allows us to do is, the queries are super efficient because we give the time range. User also said, hey, I need from 1 p.m. to 2 p.m. So we have that another slice where we can further reduce the amount of data ClickHouse has to query. So this significantly reduces the number of rows that ClickHouse has to go through to get the data. Another side benefit of partitioning by date and order by hour is it's very trivial for ClickHouse to clean up the data. So for example, as I said, we retain data for 6 months. So after 6 months, ClickHouse has to purge that data from its system. With this, what happens is all it has to do is just drop that partition that is beyond the 6-month window. Instead of, if we didn't have that, then it has to go row by row and figure out, is this data beyond the 6-month window, and then drop. But with this, it becomes very trivial to do that. Another side benefit is it helps us with the billing. So we charge customers based, for the logs, we charge based on the size of the logs that you send. And for metrics and traces, it's number of events that you send. So with partition, each partition is per day. So we count the size of that partition every day. Do it for 30 days and you have 1 month worth of size for charging for logs. And you also get the row count per partition every day, sum it up over a month, and you have events, number of events that happened over a month. So it becomes very trivial to implement the billing logic for us by partitioning by date and ordering by hour. So with this setup, what is our current performance? So as of now, we can handle 2 petabytes of uncompressed data a month across all our accounts. It's not per account, it's aggregated over all accounts. We usually see around 60K queries across all the 8 nodes per hour. This might appear less, but we have to remember that one, the agents that are running in your infrastructure who are sending the telemetry data, there is a buffering that happens at the agents, which is 15 seconds for logs and 5 seconds for metrics. And the batching service that we saw to reduce the number of inserts that happen. So that also helps in reducing the number of queries. And most of these queries are insert queries because our learnings from observability is people like to send a lot of data, but when it comes to consuming the data, it's over a narrow window. So you might send me a 1 month worth of data, but when an outage happens, you are typically looking at maybe a week's worth of data to figure out what happened. So there are a lot more inserts happening than the select or read operations. Another thing we changed is to use ZSTD compression instead of LZ4, which is default. LZ4 is the default. LZ4 is faster. ZSTD is a bit slower than LZ4, but it has better compression. The scale at which we receive the data, which is in hundreds of terabytes, every bit of savings on the storage matters. So we opted for more savings on the storage side by compromising some speed. And this is reflected in what we see in our database. So the column in the yellow shows how much compression rate we achieve on our raw data. So we have always seen it upwards of 15. The compression rate is always 15 or above with using ZSTD. Now I would like to talk about challenges. This all is great so far, so good, working great. But what are the current challenges that we are seeing? As I mentioned, we are self-hosted. So vertical scaling is very limiting. So you saw those 8 shards. What happens in each customer gets assigned to 1 shard. So if there are 2 customers or a group of customers who are assigned to same shards and heavily utilizing their ingestion or querying data, then that shard sort of starts seeing high CPU and memory usage. That slows down the inserts on that shard, which kind of then backs to the batching service, which slows down the batching service, which starts to build up our Kafka queue. And then again, that in turn slows down the inserts. And then our agents sort of throttle or start to sample the data because the ingestion rate is very slow. And then because if you remember, the Kafka partitions are shared across customers. So you might end up impacting a neighboring customer who's using the same partition as you. So these are the challenges that we see because ClickHouse is slow in processing queries or inserting the data. What are some of the solutions we tried? So one solution we have tried is adding more replicas. easy, right? I mean, logical. You add more replicas and your problem might be solved. But that's not what we observed. What happens is, given the amount of metadata that ClickHouse has, like each cluster might have in the order of 200 terabytes or more data that it is managing. So it has huge amount of metadata. So even if you spin up another replica, it's going to take a long time to become operational because it has to process all the metadata, build the metadata on its instance, and then become operational. As we have seen, it's sometimes in the order of couple of hours before it processes all the metadata and becomes operational. So clearly not very feasible, and it's especially not feasible for transient spikes of data. We can't be spinning up a replica for every transient spike. Another option we explored was adding additional clusters. Like, why have 4 shards? Just add one more shard and the problem might go away. Not so much, because all your old customers or existing customers are still on the existing shards. And those are the shards that are heavily utilized. So adding new shards, yeah, you can put your new customers to the new shards, but that won't solve the problem that existing customers are seeing. So that also was not so much of a solution. Another thing is maybe we can use ClickHouse Copier and build some tooling to migrate heavy customers to the newer clusters, so to balance the load. It works, but given the amount of data that we have to migrate, it still takes some time. So looking at all this, what we ideally need is a separation of compute and storage. It's a deep separation. Like, compute should be stateless. And we are using some of the similar principles in our Kafka. So our Kafka that you saw is not Apache Kafka, but we are using a solution called WarpStream, which is a stateless Kafka. So all their Kafka compute is stateless, and so it allows us to scale as and when we need it. So we need something similar for ClickHouse. ClickHouse Cloud has shared merge tree, which is exactly that, but unfortunately it's not yet available in open source. So and we are self-hosted. So we are exploring alternatives as to how we can achieve this separation. One option is go to ClickHouse Cloud, and it can work. For heavy customers, we can use ClickHouse Cloud and use shared merge tree to alleviate that problem. But as I said, we are exploring other options as well. Other challenge is with materialized views. So when we started using ClickHouse, we were very excited about how materialized views work, and you get these views automatically created. Whenever the data is inserted, the views are automatically updated. But we were over enthusiastic about materialized views, and we end up creating too many of them, and that kind of slowed down our ingestion as well. So that was one challenge, but we needed those views. So what are the options? I'll talk about some solutions in the next slide. And if you're not careful, materialized views can explode in size. So your select query to create your materialized views, you have to be super careful. In this case, we had a materialized view, which thankfully is no longer there, but the raw log table was around 20 gig, but the view from that log table got exploded to 190 gig, so almost 10x the size of the raw table. And this happened because, again, we were creating one row per attribute, and each log can have 10 attributes. So, you end up loading up your materialized view if you create it per attribute. So what are the solution to this problem? So one thing we did was remove if you have a lot of materialized views, remove the selected materialized views and create the tables for them instead. Now, some of the aggregations that we do are not very critical. Like, if you have a 5-minute aggregation, 1 hour aggregation already created, and then you are creating a 2-hour aggregation, maybe it can wait. So what we do is we create the tables and then periodically run a cron job to populate those tables instead of relying materialized view to go and update the table. So it's a balance between your insertion speed and how between the data recency. Again, carefully create your materialized views so that they don't explode in size. Rule of thumb that we use is your materialized views should be sparse than your parent table. And in some cases, it might be okay to, your queries to run slower for certain use cases, rather than relying on materialized view to, run the query more efficiently. One such query that we have is fetching of the filters, where you can filter your logs by host ID or server name. So that filters are fetched for a time range that you select. And it happens only once because we know the time range. But the logs for within the time range might be multiple. So it might be okay for this one-time query to be a little slower. So it's again a trade-off between running a query a little slow versus having a materialized view. And it's very use case dependent. In this case, we chose it's okay to run for this one-time query to be a little slower. Having said that, what are the future directions? Again, we are truly exploring how we can achieve separation of compute from the storage to be able to horizontally scale the compute layer for fault tolerance as well as high scalability. We are also right now in the process of tuning the batching services. Today, it's same for all three logs, metrics, and traces, 30 seconds or 200 MB, whatever happens first. But looking at the data that we have so far, there is an opportunity where we can fine-tune them per signal. Another thing that you might have noticed when I showed the diagram of shards and their replicas is everything was in one region, but different availability zones in AWS. So we are looking at cross-region migration tooling as well. Sometimes US customers want their data to be moved to Europe, and we have like a lot of compliance things that we have to follow for Europe, especially GDPR. So we are looking how we can migrate. We do cross-region migration. We have explored using materialized views that you create a destination table for a materialized view, which is cross-region, and then you populate this materialized views, which then automatically streams all the data to the destination table, which might be in Europe. So we are still in the process of doing that. So that's why I didn't share more details. And that's about it.